Here we are discussing about the topic non-parametric regression. Before that, we have to talk about parametric model. A parametric model is a statistical model in which a family of distributions with a finite set of parameters. For example, let us consider a normal regression model. The response variable y follows a normal distribution with mean x beta and variance sigma square in, where matrix of response variable, x is a n by p matrix of explanatory variables, and beta is a p by 1 matrix of regression coefficients. Since beta is a p by 1 matrix, there we have p parameters, and in addition, sigma square is also a parameter. Thus, totally we have p plus 1 parameters. That is, it is a parametric model having finite parameters. A non-parametric model is a statistical model in which a family of distribution with infinite set of parameters. Here we are consider another normal regression model having response variable y follows a normal distribution with mean f of x1 and variance sigma square in, where the function f of x1 is an arbitrary function with the range of x1 between -1 and 1. Here we have an infinite set of parameters. It indicates a non-parametric model. In general, in non-parametric regression, we can say that the mean mu y is equal to expectation of yi is a function f of xi. Some examples are given below. The normal regression and the Poisson regression is expressed as the mean function. That is, the f of x is given here. In non-parametric regression, the set of possible fits to the data is much larger than the parametric approach. In parametric regression, first we fix a line and check whether it is the exact fit. If it is not exact, then we introduce some higher order terms like squared, cubic, etc. That is, we fixing the data model initially and then check whether that is a good fit. If it is not a good fit, then we can change the form according to the fit. Next, we are discussing the advantages and disadvantages of non-parametric regression. Non-parametric regression is very flexible. If we didn't have any past information about the data, that is, the form of the data like linear, squared, cubic, etc., the non-parametric regression is more flexible. Since the non-parametric regression is not consider the distribution of the data, it is less possible to make mistakes that result in bias. The disadvantages are, if we have any idea about the data like the degree of data, the non-parametric regression is less efficient, and also there are some interpretation difficulties. Now we move on to the estimation procedures. From figure 1, we can see that there is no linear relationship between response and the predictor. That is, the relationship is non-linear. A better way to diagnose non-linearity is considering residuals versus fitted value plot. And the figure 2 indicates that. In the figure 2, we can see that there is a non-constant variance between variables, smaller variance in left and larger variance in right. From these two figures, it is clear that it is neither a simple linear regression model nor a multiple linear regression model. So, for evaluating the exact model, we have to add polynomial terms to it. That is, we have to change our model to yi equal to beta naught plus beta 1 xi plus beta 2 xi square plus etc. plus beta d xi raised to d plus epsilon I, where d is the degree of the polynomial that we have to fix. Now, we have to choose d. Here we have two methods to find d. The first method is to start at d equal to 1 and add terms until they are statistically significant anymore. That is, introduce d until specific d is occurred. The second method is to start with a large d and eliminate terms that are not statistically significant. But it is a bad idea. For example, to eliminate x square but keeping an x cube term in it, that is, we have no idea about the degree of the model. If we choose d randomly, there is a possibility for terms higher than d will be statistically significant. In this example, we get that d equal to 1 and it is a simple linear regression model while using the method 1. But we know that it is not correct. The second method suggests a degree for polynomial and the exact fit. Suppose we have two predictors. We have to find d1 and d2 corresponding to each of the predictors. But it is not easy. So we have to use other methods like kernel smoothing and smoothing splines. Therefore, now we are discussing about the kernel smoother. Kernel estimator is a simple weighted local moving average of the response. Let consider the model yi is equal to f of xi plus epsilon I, where f of xi is an unknown function and epsilon I follows normal 0 sigma square. Since f is unknown, we have to estimate f from the data. The kernel estimator of f is given by the first equation, that is by f lambda cap of xi, where k and lambda are weights and we can discuss about it later. If we consider wi equal to 1 by lambda k of x minus xi divided by lambda, then our f lambda cap of xi gives 1 by n summation I equal to 1 to n wi yi divided by summation I from 1 to n wi, and this is our estimated kernel function. Now we can discuss about the kernel. A kernel is a non-negative real-valued function k such that k of x equal to k of minus x for all values of x and integral of k of x dx equal to 1. Since the non-negative and integral properties are satisfied by the density functions, the density functions can be taken as kernel. Some commonly used kernels are uniform or rectangular, 2. Gaussian or normal, 3. Epanechnikov. So we have mentioned that we have another weight called lambda is known as bandwidth. The bandwidth or smoothing parameter controls the smoothness or bumpiness of the estimate f cap. Smaller lambda gives bumpier fit and larger lambda gives smoother fit. That is, as lambda increases, smoothness increases. In figure 3, the black curve is with bandwidth 0.1 have a bumpy and sensitive curve. The grey curve has bandwidth 2 is much more reasonable and smooth curve. And the gold curve has bandwidth 10 is too smooth like a line fit. That is, if lambda is very small, the curve will be very rough. And if lambda is very large, important features may be smoothed out. The bandwidth is calculated using cross-validation method. Next method is smoothing splines. Firstly, we can go through some definitions. A spline is a piecewise function where each segment is a polynomial. In figure 4, the orange color line indicates a linear spline. A cubic spline is a spline where the segment polynomials are each of degree 3. In figure 4, the green color dotted line indicates a cubic spline. A smoothing spline is a spline designed to balance fit with smoothness. And in figure 5, dotted line represents a cubic spline and the bold line represents a cubic smoothing spline. Smoothing spline get the smaller curvature due to restriction of derivatives. Let us consider the model yi is equal to f of xi plus epsilon I. We know that the mean square residual is MSE equal to 1 by n summation I from 1 to n yi minus f of xi the whole square. Now we can estimate f by minimizing the function delta where the second term is called the roughness penalty and the lambda is a positive real number called smoothing parameter and the first term is the MSE. Here, the first term controls the fit and the second term controls the smoothness. If f double dash of x is 0, then the minimizing function will become MSE, but it will give information about a line. Since our objective is to model non-parametric regression, does it need a linear structure? Thus, f double dash of x must be non-negative. Lambda determines the smoothness and it is calculated by cross-validation method. The solution to the above model is a cubic smoothing spline. And that's over. Thank you.